This question evaluates your circuit skills, resistance of a wire, and drift velocity with 14 total points for one question. You need to know how to write Kirchhoff's second law definition, analyze resistors in parallel when they have equal values, the effects of batteries connected in parallel, and how to calculate current using Ohm's law. Also, you need to know how to calculate the resistance of a wire in terms of resistivity, length, and cross-sectional area using this formula, and how to calculate the drift velocity of electrons in a wire using this formula here, however, rearranged in terms of the drift velocity. Question A is state Kirchhoff's second law. The sum of EMFs is equal to the sum of PDs around a loop. Question B. Three identical cells, each of electromotive forces EMF 1.5 volts, internal resistance 590 milliohms, are connected in parallel across a conductor, as shown in this picture. The conductor is composed of two cylindrical sections, A and B. The total resistance of the circuit is 2.2 ohms. Show that the resistance of this conductor is 2 ohms. All internal resistance are equal to 590 milliohms and connected in parallel. To calculate the total resistance of the internal resistances is 590 milliohms divided by 3. So the total internal resistance is equal to 197 milliohms. The question states the total resistance of the entire circuit is 2.2 ohms. So we can say that the resistance of the conductor R is equal to the total resistance of the circuit, which is 2.2 ohms, minus the value of the total internal resistance, which is 197 milliohms. So will be 2.2 ohms minus 197 times 10 to the minus 3 ohms, which is equal to 2.003 ohms. Rounding this number, R is equal to. The question is answered. Question II. Calculate the current in the conductor. Here is a junction. In this parallel arrangement, the current from the batteries, all three, adds up by the junction in this red dot and flows through this conductor AB. For this reason, the current in the conductor can be calculated using the total resistance of the circuit. To summarize this circuit here, I draw this one for you. 1.5 volts in parallel, and the total resistance of the circuit, which is 2.2 ohms. So this is the voltage, and this is the total current of the circuit. So the current can be calculated by V over R, which is Ohm's law for current, 1.5 divided by 2.2, and we have a current equal to 0.68 amps. So So this is the current that is flowing through the conductor. Question C. The two cylindrical sections A and B of the conductor in figure 5.1 are made from the same material and have the same length. The diameter of section A is 4.3 millimeter and the diameter of section B is 7.6 millimeter. The resistance of section A is RA and the resistance of section B is RB. Calculate the ratio RA-RB. I'm using the formula resistance of a wire, which is equal to resistivity of the material times the length of the wire divided by the cross-sectional area. So this is resistance of the section A, and this is the resistance of the section B. The question is saying that both conductors are made of the same material and have the same length. So resistivity and length are the same. So when I have RA over RB, I can cancel resistivity and length because they are the same. So what is left is the cross-sectional area. So on the numerator, I have 1 over the cross-sectional area for the section A and over 1, and here we have a fraction, 1 over the cross-sectional area for B. So in this case, I'm multiplying and flipping the fraction that is on the denominator. So this is what I have. Now the area of a circle, which is the cross-sectional area, is pi times radius squared, or pi over 4 times diameter squared, because diameter was provided. Now, because pi and pi here is going to be canceled, pi over 4 on both areas, I'm using just the diameter. So here the diameter of section A is 4.3 and section B is 7.6. So since the diameter is square, so it's 1 over 4.3 square times 7.6 square. So this ratio is equal to 3.1. 3.1 right here. Now this question is asking to calculate the ratio of the average drift velocity from section A and section B, and explain my reasoning. I'm going to use the current of a wire formula, at which I is the current in the wire, A is the cross-sectional area, N is the number of free electrons, V is the average drift velocity or speed, and Q is the charge of an electron. Now from this formula, I'm going to rearrange for the drift velocity. So V is 1I over A and Q. Because both cylindrical sections A and B of the conductor are made from the same material and have the same length, imply that current, the number of electrons, and the charge are equal. This is helpful because allows cancellation of these values for the ratio drift velocity in both sections, and I'm going to use just this formula here. V is current over A. So here we have VA over VB. VA over VB is 1 over cross-section A, and then I will flip this value here just like I did with resistance from both sections in the prior question. And I will have the same result, 3.1. Some additional notes about this question. Knowing that section A diameter is 4.3 millimeter and section B diameter is 7.6 millimeter, the results from I, the resistance of section A is 3.1 times greater than the resistance of section B. And from this section here, double I, the drift velocity on the section A is also 3.1 times greater than the drift velocity of section B. This indicates the resistance of section A, which has the smaller diameter, has greater resistance and greater drift velocity than section B, which has larger diameter. Last question, D. The circuit from figure 5.1, which is this one, is altered by removing one of the cells. Boom, one is gone. State and explain the effect, if any, of this change on the potential difference across this conductor. Below is the sequential effect on the conductor. The first one, because a parallel resistance was removed, then the total circuit resistance increases because it's in parallel. The second one, because the resistance increases, talk about the total resistance, the current in the conductor decreases. And the PD across the conductor, it decreases. So because the total resistance increases when we remove one of the parallel battery, the current in the conductor decreases, and so its PD. Now the PD is 2 ohms times less current.